One of the most incredible but also kind of frustrating things about our universe is just how big it is. I mean, it's huge. We can see all these new worlds out there, but the real question is, can we ever actually get to them? Well, today we're going to explore a wild idea, one that's actually backed by science that could change everything: cosmic shortcuts.
And this really is the ultimate question, isn't it? If we want to be a true spacefaring species. Right now, for all practical purposes, we are totally stuck in our home galaxy, the Milky Way. Leaving it? I mean, it feels like an impossible dream. But let's look at the numbers to see why it feels so impossible.
Okay, so here's the scale of the problem we're dealing with. Our closest big galactic neighbor is the Andromeda Galaxy. It's 2.5 million light-years away. Now remember, that means light itself, the fastest thing in the entire universe, takes 2.5 million years to make that one-way trip.
So what about us with our fastest spacecraft, like the best technology we have right now? It would take us a mind-blowing 94.5 billion years to get there. That's older than the universe itself. A journey that long is basically meaningless. So you have to ask, what if there was another way?
And this is where the rules of physics start to get really, really weird and fun. What if you didn't have to travel across all that empty space? What if you could just punch a shortcut right through it? That's the wild idea behind something called a wormhole.
Yeah, a lot of us have probably seen this in the movies, right? I'm thinking of Interstellar. A team of astronauts travels to a whole nother galaxy, not in billions of years, but in like a few minutes, all thanks to this mysterious tunnel in space. It's such a cool sci-fi image.
But here's the thing, and this is the crucial part. The idea of a wormhole isn't just something Hollywood made up to move the plot along. No way. It's a concept that comes directly from the fundamental laws of our universe, described by one of the greatest scientists who ever lived.
So to really get where this whole wormhole idea comes from, we got to go back to the source, Albert Einstein, and his revolutionary theory of general relativity. And it all starts with a set of really, really powerful equations.
These right here are Einstein's field equations. Basically, they're the rule book for gravity. What they showed the world is that huge things like planets and stars don't just sit in space. They actually bend and warp the very fabric of space-time around them. It's pretty wild.
Now, to get how these equations work, just think back to high school algebra for a second. Remember quadratic equations? Something like x squared minus 5x plus 6 equals 0 actually has two right answers. X can be 2 and x can be 3. Both are totally correct. Well, in the same way, Einstein's equations, which are way more complex, also have multiple equally valid solutions. And these solutions, they describe real things out there in the universe.
So what are these different solutions? What do they describe? Well, one of them predicted the existence of black holes, an idea so strange it took us 100 years before we finally got a picture of one. Another solution describes something just as bizarre, a wormhole. And a third describes its weird twin, a white hole.
Okay, so we've got the math, the blueprint, but how would a wormhole actually work as a shortcut? To get that, we have to start thinking about the shape of space in a whole new way.
This is the perfect way to picture it. Imagine you have a flat piece of paper. The shortest way to get from point A to point B is a straight line, right? But what if you could use a third dimension to just fold the paper over? Suddenly, A and B are right next to each other. You can create a bridge that makes the trip almost instant. A wormhole is basically proposing we do the exact same thing, but by folding our three-dimensional space through some theoretical fourth dimension.
And this specific idea, this mathematical bridge through spacetime, was first figured out by Einstein himself and his colleague Nathan Rosen way back in 1935. That's why you'll sometimes hear it called an Einstein-Rosen bridge.
But the name that really stuck, the much catchier name wormhole, came a bit later from a physicist named John Wheeler, and he had this fantastic analogy for it. Imagine a worm on an apple. It can crawl all the way across the surface, or it can just take a shortcut and burrow right through it. That's exactly what a wormhole is supposed to do to the fabric of spacetime.
Okay, so if it's a tunnel, it's got to have two ends, right? You need an entrance and you need an exit. So, what in the universe has enough gravitational power to rip open an entrance to a tunnel through space-time itself?
Theoretically, the answer is a black hole. Its incredible gravity could be the entrance, just sucking everything in. But there's a problem. If you have a black hole on both ends, it's not a tunnel, it's a trap. You go in, but you never come out. So for a real exit, the theory says you need its exact opposite, a white hole, a hypothetical spot in space-time that violently shoves everything out and lets nothing in.
All right, so we have this amazing theoretical picture, right? A black hole for an entrance, connected to a white hole for an exit, making a tunnel you can travel through. Now we get to the most important question of all. Does any of this actually exist anywhere besides on a blackboard?
And this is where we have to come back down to earth a little bit. The reality is, for now, wormholes are purely theoretical. We have never ever seen one. And white holes, they're even more out there. A lot of physicists think they just can't exist because they seem to violate some really fundamental laws of physics, like the second law of thermodynamics. And even if they did exist, we have no clue if they'd be stable enough for anything, even a single particle of light to pass through.
But just because the classic gravitational wormhole is still a dream, that doesn't mean the story's over, not by a long shot. The basic idea of a shortcut is just so cool that scientists are now looking for it in other, very different areas of physics.
Check this out. In 2015, scientists did something incredible. While we can't find gravitational wormholes, they actually created a magnetic wormhole in a lab. It was this device that took a magnetic field at one point, made it totally vanish from the space in between, and then popped back up at another point, almost like it tunneled through an invisible dimension. Now, you can't travel through it, but it was the first real-world proof that this shortcut idea is physically possible.
And the ideas don't stop there. Other concepts for faster-than-light travel also coming out of Einstein's equations are being looked at. Take the Alcubierre drive. The idea here is that a ship could ride a wave of space-time, scrunching up space in front of it and stretching it out behind. So the ship itself never breaks the speed of light, but its little bubble of space-time would. Pretty clever, right?
Which really brings us right back to where we started. For over 100 years, this one set of equations has given us black holes, the mind-bending possibility of wormholes, and all these brand new ideas for how we might one day explore the cosmos. It just makes you wonder, doesn't it? What other incredible secrets about our future are still hidden inside them, just waiting for us to find?